Hi everyone, we are Group 5 from Lab L2G. Today, we will be presenting our neural network project where we focused on building an efficient and accurate lane detection model. Each of us will be explaining our individual contribution to the project, highlighting the key decisions and work that went into making it successful. My main contribution was focused on collecting high-quality data and optimizing the model for performance and efficiency. I collected a total of 80,000 images by merging multiple data tracks to ensure we had diverse and balanced dataset. From that, I used 50,000 images for training and 30,000 for testing to get a solid evaluation of the model's generalization. Throughout the process, I made sure that data was free from major biases, which is crucial for building a fair and reliable model. I also worked on keeping the model architecture simple and efficient, making sure the final size stayed under 20 MB limit. After several iterations, we achieved a final model size of just 1.78 MB. To improve performance, I tested different activation functions. Through trial and error, I found that ReLU gave us the lowest validation loss, helping us strike a great balance between accuracy and simplicity. Overall, my focus on building a strong foundation through quality data and efficient model design, and I'm proud of the results we achieved.
All right, so for me, Sam, my contribution to the group was that I was responsible for selecting how many convolution layers and how many max pool 2D layers we had in our final model. So the way I went about doing that is that I started with just one convolution and max pool 2D layer, and then I ran the model, saw the MSE, and the MSE wasn't very good. So I basically just kept trying different combinations. I would try maybe 2 convolution and 2 max pool D with, certain size, certain amount of neurons in each. It was basically just trying different combinations. And yeah, after a lot of trial and error, I came onto the final model that we have. And in our final model, we have 3 convolution layers and 3 max pool 2D layers. With the convolution layers, we have 128 neurons, 64 neurons, and 32 neurons. And yeah, I found that from this selection, we had the best performance. And in the screenshot you'll see on the screen right about now, you can see that we were able to achieve a very low MSE, about 2.8, 2.9, which is very good.
Choosing the amount of neurons per layer was a tedious job. This required lots of time and error. The balance between using enough neurons but not too many was hard to find. By using more neurons per layer, there would be more connections for the model, but by using too many neurons, this would slow the process of training our model. Since we were on a time crunch when creating the final model, too many neurons would result in an inefficient use of our time. Originally, my idea was to use as many neurons as seemed reasonable, but quickly saw how long it would take to get through training the model. For this reason, I started to play around with using less neurons and collaborating with David and Sam a variety of different amounts of convolution layers and dense layers. We began having the most success with 3 convolution layers and 5 dense layers with no more than 128 neurons at most. Using 128 neurons and going down incrementally by half without skipping any values, we were able to achieve our lowest validation loss. More simply put, in our convolution layers, we use 128, 64, and 32 neurons, and in our dense layers, we use 64, 32, 16, 8, and finally 1 neuron for our output layer. This gave us our final model, which achieved a validation loss of 2.8, and ultimately became the proud model that performed perfectly on all of the given tracks on testing day.
Hello, my name is David Bra, and I'll quickly be explaining my contributions to our final model selection. My main focus was on optimizing the dense layers, epoch, and learning rate to improve model performance. I experimented with hundreds of epoch and learning rate configurations, testing values from 10 to 150 epoch, and learning rates ranging from 0.5 to very, very small increments. After multiple trials, I determined that 15 epoch with a learning rate of 0.001 using the ADD optimizer provided stable conversions without overfitting. For the dense layers, I tested many different structures and neuron counts, ranging from 8 to 512 neurons. I finalized with 4 dense layers, including 164, 32, 16, and 8 neurons respectively, each using the redo activation. This setup improved the model's ability to learn patterns while keeping it lightweight. By fine-tuning patterns like these hyperparameters, I helped ensure that our model was both accurate and efficient.
Our model has 3 convolutional layers, 3 max pooling layers, and 4 dense layers, with a final linear output trained for 15 epochs at a learning rate of 0.001. It also achieved a mean squared error of 2.8418 and performed both well in simulation and real-world tests. Its compact size also made it very easy to deploy. Overall, it is a reliable and well-optimized solution. Thank you.